All right, hey guys. We're looking at a quiz Tuesday. I said Tuesday, right? Um, so hopefully you'll get some studying in Sunday, and we'll talk in class Monday, and you'll be good to go. But I'm going to go over the homework and the extra practice, and then you can hit me up with whatever questions you still have. But let's get into it. This is number one from the homework, and you'll see that it's asking for an integral whose lower limit is zero. So we know we're looking for an integral whose lower limit is zero. That much is sort of obvious, I guess, but how do I figure out the rest from here? And the answer is you kind of need to have the general form of these summation notations memorized. So we know that they will all be the limit as n goes to infinity of the summation of a bunch of stuff as k starts at 1 and goes up to n. Now, what's the stuff we're looking at? Well, this n, or this pi over n, is delta x, which is b minus a over n. So that whole thing there is delta x. Then the next thing, it should be f of an a value, which is our lower limit, plus the same delta x, b minus a over n, multiplied by k. So I don't know how confusing this is about to be, but this stuff here is this stuff here. And all this stuff here is this stuff here. Okay, so how do I kind of pull this apart then? Uh, well, the fact that this numerator up here, this pi, that's b minus a. And we know that a is our lower limit, which had to be 0. So to get a pi, wouldn't that mean b had to be pi? That all is because the width of our interval is pi. So that's how we can kind of quickly figure out that the upper limit of integration is pi. It has to do with the difference between those numbers having to equal that number there. It's got to be pi. Now, in terms of what's our function, I think it's kind of a no-brainer that our function involves cosine. But with all this other stuff sort of inside there, it's the cosine of what? Now, often it's just plain old cosine of x. But for slightly more complicated ones, you could have cosine of 2x or cosine of x plus 4 or whatever. But think about it like this, I guess. All this stuff in parentheses is x. And so try to pull this thing apart up here. Like, what is up here? What is in these parentheses? Well, we know the lower limit of integration was 0. So we had a 0. That disappeared because 0 plus some stuff doesn't matter. But then that's plus pi minus 0 over n times k. So if you look at all this, there's nothing left. Everything is sort of accounted for. The a is 0. Pi minus 0 over n is something. K is something. So all that stuff is just part of the expression that equals x. So everything in there is really just our x. So there's nothing else to account for. It's got to just be cosine of x. And then lastly, just with every integral, make sure that you include that differential at the end. So since our variable is x, we'll put a dx. But that's it. I hope this felt like an easy one. And let's try to hit some harder ones that maybe are more complicated. So here's number 2, doing the same thing. We still want the integral. It says we want a lower limit of -3. And again, if this piece here is delta x and the numerator is supposed to represent the width of our interval, then you just take 5 and add it to -3, and we land on 2. That would make the width of our interval 5. Then I certainly see an outer function that certainly looks like the cube root of something. Now, is everything under here accounted for? Well, this is my a plus 5 over n. If I just kind of move the k over to here, 5 over n is my delta x times k. So yeah, all that stuff is just x. There's no like plus 7 on the end or squared or anything else. So there's nothing else under the radical that we have to account for. It is just the cube root of x dx. And that's that one down. 3. So 3 is another one. We're going to do the integral with a lower limit starting at 6. the upper limit of 9, again, it doesn't mean we put a 9 here. That would mean the width of our interval was only 3. We want the width of our interval to be 9. So you have to add 9 to 6 and go all the way up to 15 so that your width is 9. Then looking at this, here's the 9 over n. So here's my a plus delta x times k. So all of that stuff, that's the stuff that kind of becomes our x. And so we can see that our function is just 1 over x squared dx. That's that. I think here we switch. I think I don't know, I don't want to jump around, I guess, but while we're kind of hot on these ones here, why don't we keep going on this kind of thing where we're going from limit notation to integral notation. So I'm going to skip over 4 and 5 and 6 and 7 and 8 and 9, and we're going to go all the way to the extra practice, and we'll just tackle these while we're doing problems of the same type. So looking here at the extra practice, let's do number 1, the first number 1. It again says the integral's lower limit is 0, so we'll start at 0. Oh, right. Okay, so the pi over 4n might be throwing you a little bit, but pi over 4n, that's equivalent to pi over 4 over n, if you think about it. Or even if you don't think about it. But think about it like this. If you didn't want this compound fraction, then you'd multiply the bottom by its reciprocal, 1 over n, and then you'd have to do that to the top. And then the n's, all that stuff in the denominator would cancel, and you can see that this is equivalent to pi over 4n. So if that's written in a way that you don't particularly like, you could kind of just reimagine this as, all right, this is a pi over 4 over n, and all that stuff is your delta x. So that's telling you that they want the width to be pi over 4, so your upper limit of integration has to be pi over 4. Now that also means that as we head over here, this pi over 4 over n and a k, all that stuff is sort of what we expect to see. Now there should be an a plus here, but the a is 0 anyway. So if everything here in parentheses was 0 plus pi over 4 over n times k, then we know that all that stuff for us is just our x value. So again, this is kind of a super simple integral. It's just going to be the integral of tangent of x dx. Hopefully we're going to see something with something else involved here, but maybe not. All right, number 2 says we want the integral whose lower limit is -1. Again, this 8 represents the width of our interval, so I guess we have to go to 7. And there's not much of a function here, but this -1, that's our a value. We can spot the 8 over n as our delta x times k. So if we kind of just turn all that into x, then we've got a pretty simple function here. It's literally just the function for x dx. And that's our whole integral there. What about number 3? Well, there is no 3. We're going to go back to 1 and 2 on the second assignment. So how's this guy look? This guy wants to start at -1, have a width of only 2, which means we go to 1, so -1 to 1. And again, I'm spotting my a value, my 2 over n times k. So this whole thing is just the function x to the 4th dx. So there's your integral notation. And lastly, number 2 is going to ask us to do an integral whose lower limit is -7, whose width is 4, so we're going to only come up to -3. And again, everything's kind of present and accounted for. We've got our a value. There's our delta x times our k. So it is just the coefficient of plain old x dx. So that's that. Let's go way back now to the original homework. and we did 1 and 2 and 3. So now we can switch gears and talk about how to do this the other way around, is turn these integrals into summation notation. So for summation notation, it's always going to be the limit as n approaches infinity of some sum where k starts at 1 and goes up to n. Then we want our, well, I'll just write out the formula again. But b minus a over n will give us our delta x. Then we want to multiply that by the function that we are given, in this case x squared, evaluated at a plus delta x, which is b minus a over n multiplied by k. So this is sort of the general formula that we want to do every single time. And that means we want the limit as n goes to infinity of a big sum where k starts at 1 and goes up to n. Now b minus a over n is just going to be 3 minus negative 3. So 6 divided by n. And then since our function is x squared, just open up a big old set of parentheses, put a squared on it, and then just fill all this stuff in, including the k, sorry. But the a means we want to start at negative 3. Then we want to add to that our delta x, which is 6 over n. And we want to multiply that by k. And if you want to put the k in the numerator with the 6, be my guest. If you want to kind of leave the k out over here as like as just something you're multiplying by, that's fine too. And I would leave this, I would leave this alone. We don't put dx on the end of this. We only put dx on the end of integrals. Because dx, by the way, if you didn't hear me say this before, dx is literally the same as delta x. And our expression already has delta x built right into it, right? The 6 over n is the delta x, so we don't need a dx to represent it because it's already in there. And the other thing I was going to say was don't bother foiling this out. It's fine to just leave it in its factored form. In fact, it's preferable to do so. So leave your answer just like this. And let's try 5. So for number 5, I'll skip some of the setup and just go right to the answer. But you know it's going to be, started to draw the wrong thing. You know it's going to be the limit as n goes to infinity, that ain't changing, of the sum that starts from k equals 1 and goes up to n, that's not changing. And for this problem, since our limits of integration go from 2 to 5, we know that 5 minus 2 gives 3. So 3 over n will be our delta x piece. And then the function is 1 over x. So we're going to be looking at a 1 over, and for us x always wants to be that lower limit of integration, which is 2, plus delta x times k. Delta x is still the 3 over n, the same thing that we just wrote, times k. But that ought to do it. This is the one that I said in class we probably should kind of imagine simplifying, because if you're multiplying two fractions, you just multiply the tops and you multiply the bottoms. And for us, this n will distribute into this, and it will actually clean us up a little bit. So I think the best form of this answer would be the limit as n goes to infinity of the summation that starts at k equals 1 and goes to n. And again, all this, your numerator is just 3 times 1, so we get a numerator of 3. And in the denominator, this n would distribute, giving us 2n plus. Now when the n distributes here, it cancels, and so you just get 3k. So to me, that just looks a lot nicer and much more simplified. So this would really be the form that I'm looking for right here. And then we can try 6. So for 6, oops, I keep doing that. So we're starting with an integral, so we want to go to summation notation. So we know we want the sum of stuff that starts at k equals 1 and goes all the way to n. We know we want the limit of this sum as n goes to infinity. We know we want delta x, which is 7 minus 0, so just 7 over n. And we want to multiply that by the function, which for us is a big square root. And we want to evaluate it at a, which in this case is 0, plus delta x times k, so 7 over n times k. And of course, you'll never leave 0 plus something as part of your final answer. So it's really just the 7 over n times k. And that's all we need to see under the radical. So 7k over n is fine if you want to express it that way. And then because I was able to simplify, my radical doesn't need to be so long. But there you go. This doesn't really simplify in any great way, so we'll leave it just like that, call it a day. So before I move on to 7, again, let's go out to those extra practice problems. Maybe I can color code this or something, but these will be the extra practice pages. Whoops, I don't know what I'm doing. All right, anyway, remember we did these ones. And so let's do these ones now. Just while we're on one type of problem, let's do them all. All right, so again, on the extra practice pages, we're looking at numbers 3, 4 from the first, and then 3, 4 from the second, 2 different sheets. So write a summation notation. All right, fine. So we're going to go limit as n approaches infinity of the sum as k starts at 1 and goes to n. And again, just do b minus a, subtract those limits of integration, you get 4. Divide that by n, there's your delta x. Then multiply that by the function, which for us again is just x squared. So what are we cramming in here? What crams into there is the a plus, I guess technically it's delta x times k. That's all the expression is. But for us, that's a plus b minus a over n times k. So again, pretty straightforward. Our a value is -1. So -1 goes in. Then we're adding to that 4 over n times k, or 4k over n. And we could simplify that a little, I guess, but you don't need to feel like you need to. You know that if it were me, I'd probably do 4k over n, and then just move the -1 to the end, because I hate those leading coefficients. Then if I am cleaning up, you might want to just turn the 1 into n over n, so then you could combine this to 4k minus n all over n. That might be the best way to express that thing that's on the inside, but again, it's not worth it, so we'll just leave it alone. So that answer right there is fine. And what about 4? 4 is going to end up being the limit as n goes to infinity of the summation from k equals 1 to n. Let's see, 4 minus 3 is only 1, right? So that'll be 1 over n. And then multiplied by the ln of the lower limit 3 plus delta x, which is 1 over n times k, so really just k over n. And that sigma notation ought to do it. Worth cleaning up? I would say no. Moving on. All right, so 2 more of these. This is going to be the limit as n goes to infinity of the sum. It starts at k equals 1, goes to n. All right, and again, what's going inside here? We want the 4 minus 1 giving 3 over n. That'll be our delta x. Then we want to multiply that by, it's 1 over x cubed, so 1 over some stuff cubed. And again, the stuff that goes inside the parentheses is the lower limit 1 plus delta x times k. So 3 over n times k. And again, don't feel like you need to clean it up. Just leave it as is, and that's perfectly fine. And then the last problem like this will be the limit as n goes to infinity of the summation from k equals 1 to n. All right, 2 minus -1 is a width of 3. So 3 over n is our delta x multiplied by e to the x. So that'll be e all to the power of that big old expression starting at a, so negative 1, plus delta x 3 over n times k. Could this be cleaned up in a meaningful way? I'd say kind of, but I'd say it isn't worth it. So I'm not gonna. But just to show you guys, because I think you guys can always use another refresher on how some of this algebra works. But let's say I'm just gonna take this expression here. The 3 over n, I'm not doing anything with that just yet. But you guys might want to remember that e to the negative 1 plus something. Well, remember the rule that base to some power times base to some power. Don't you keep the base and add the powers? So as soon as I see this plus sign, you might think about breaking this down to two separate exponentials, where you just have e to the negative 1, and then you're multiplying that by e to the 3 over n times k. And why would I do that? Well, because now e to the negative 1 can just become 1 over e to the 1. So now this guy is down in the denominator, and we just have a cleaner numerator. I don't know. You guys can tell me if you think this is actually cleaner, but it looks like to me upstairs we just have the 3, the 1, and this other e expression. So you'd have 3e to the 3 whatever. Let's call it 3k over n. That looks a little better. Okay, and then let's put that all over just n times e. Yeah, I don't know. Is that better? Probably not. And again, I'm not going to make you guys simplify anything. So remember, you can leave your answer like this green answer that we landed on in the first place. And there's nothing wrong with that. All right, moving on. Okay, so it's time to tackle these problems. Again, this is from the extra practice, so we'll save that for later. This looks like a lot. Okay, great. So heading back to the original homework, let's tackle these other kinds of problems. So again, what's a little bit weird here is you're basically given summation notation, but not really. Like they're certainly giving you the limit as n goes to infinity. But instead of asking you to do a sum where we start at k equals 1 and go all the way to n, no, actually we are going all the way to n this time. This one is infinite. So we are going all the way to n. But how do I model these expressions? Well, it certainly looks like it's got an e in it. It's an e to the 1 plus 1 over n, but the next one's 2 over n, so it's something over n. And you're noticing these are counting 1, 2, 3. Now who does that for us? Who starts at 1 and counts up, up, up? Well, that's the k variable. So that would be our k right there. And so there this is sort of expressed just like it was expressed in the older problems that we were doing. And so what does any of this mean? Well, it says which of the following is equal to? Well, I'm going to leave this as a multiple choice. I know in class when we did it we said pretend it wasn't multiple choice, but let's do it because then at least you'd have to think about it. Who's got the correct lower limit of integration? Well, normally the lower limit of integration is this value here. Am I missing something? Yeah, I had a feeling I was missing something. All right, the 1 over n, that's your delta x. Don't forget about that like I did. There is a 1 over n here. So that's part of our delta x. That's telling me that the width of my interval is 1. And then this one here, that's typically our a value. So that's telling me that we start at 1. So I'm looking for an integral that starts at 1 and has a width of 1. So it should be going from 1 to 2. And there are two options that go from 1 to 2. But let's quickly remember, you don't have to start at 1 and go to 2. We said we could kind of mess with the function rule, and it might be the one that starts at 0 and goes to 1. It couldn't be the one that starts as, well, yes, it could, because yes, we did. We did talk about how we could fart around with the function to change the width of our integral. So really, we have to be checking for everything. My heart says it's probably b, though, because, I don't know, that seems simplest, right? So what happened? We started at 1, have a width of 2. That covers everything here. Now, if all that's true, and if we're starting at 1, then the function here would just be e to the power of, well, that's my a. Now I don't see a 1 here, but there's a 1 there, and 1 overruns my delta x. That's it. Yeah. So this does boil down to just the simplest version of our function e to the x dx. So it is b. But again, what if we had wanted to just go from 0 to 1, right? What would that change? Well, wouldn't the whole graph just be shifted 1 unit to the left? And to shift 1 unit to the left, we would just have to put a +1 in our exponent. So if we had this option and this guy had, I don't know, let's say this guy had the +1 on it also, then b would no longer be right, but a would be right, because it's got a shifted function, but the interval shifted with it. So to be integrating this function on this interval would actually be the right way to go. So that's one of the more confusing things from this lesson, is how to shift these intervals around and then have to mess around with the function. But I'll keep talking about that, and hopefully that'll make more sense. Let's do the next one and see what we see in there. But looking at this again, really similar problem. The 3/7 is serving as our delta x. So we know we're still looking at the limit as n goes to infinity, well, sort of the summation of things that start at 1 but go to, well, this is the one that doesn't exactly go to n. So how many expressions do you see here? Well, I see one starting at 3/7, but then 6, and then 9, and then it's dotting all the way to 21. So how many steps did it take to get there? Is there an easy way to figure this out? Kinda. Delta x, this 3 in the numerator, that's 3 is telling us what to step by, right? So if we started at 3, then this is 1. Then we step by 3 and get to 6. So that's 2. Then we get to 9. That's 3. From 9, what's about to happen? We'd have to go from 9 to 12, 15, 18, 21. So if I kind of just continue counting those off, here's the first one, second one, third one, fourth one, fifth one, sixth one, seventh one. So there must be 7 steps here, right? Which actually, we knew that, because that's the meaning of this bottom number, right? This is what we're stepping by in the numerator. We're stepping by sort of 3 at a time, but we were using 7 intervals, the 7. Why do I say that? Well, only because in this particular problem, we're not really doing the infinite sum. We're just doing the sum of the first 7. So it's not really an infinite summation. It's a finite summation, but that's okay, because we can still pull everything out just from what we know. So what goes in here? We need the delta x, which is 3/7. Then we need our function. And what's our function seem to have? Well, this 3/7 would distribute in onto everybody. So these coefficients that you're seeing of 3/7, that's not just delta x. That is like another whole coefficient. So what is that coefficient? Well, what else is going on here? What are we looking at there? What are we looking at here? All right, well, thinking back to how this is supposed to work, we're supposed to normally see some function. We can tell it's the sine function. And normally what we'd want to see on the inside is our lower limit of integration a plus our delta x. which we know the delta x is 3/7 times k. And so looking at all the answer choices, they all have that lower limit of 0, which kind of makes sense because looking at all these expressions here, there's no thing plus 3/7. So this a kind of has to be 0. Then, well, as k is doing the counting, you're going to get 1 3/7 and then 2 3/7 and then 3 3/7, which is why we see 3/7, 6/7, 9/7. So essentially, well, yeah, this whole thing is just x, is just the sign of x. And then notice that all these coefficients are matching these inputs. So basically you've got thing and then sign of same thing, and then thing and then sign of same thing. So this 3/7, we would model that just with another x. So the thing that we're summing, the thing that we're doing the summation of, I guess, is x sine x. And so the top two have x sine x. This first one is incorporating another whole factor of 1/7 though, which I don't think we want that. So I guess the obvious choice then is A. Which, yeah, that seems right to me. So A is an apple. I'm calling it A is an apple. Okay, so from there we'll move on to 9. And 9 is almost exactly the same as the one we just did. So let's again try to break this down. So we know that what we're looking at is a summation, but it's not an infinite summation anymore. Again, we know that in this problem would be doing the sum of the first term out to the, well, I can literally see them all. It's 1, 2, 3, 4, 5 terms. But even if they did the dot 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 thing and didn't show us the fact that there was 5 terms, we would know by looking right here at our delta x over n expression that there's 5 things because the denominator was 5. So that's great. I've got that part. Then I know that in my summation I would want my delta x, which would just be the 1/5 kind of distributing in. So there'd be a 1/5, and then multiply that by the function, which pretty obviously needs to be an ln. And then inside the ln, our x variable would be our lower limit of integration. I'm seeing 2, 2, 2, 2, 2. So it would make sense that the lower limit of integration is probably 2. Then you're adding to that your delta x, which is 1 over 5, technically times k, but that k again is just ticking up from 1 to 2 to 3 to 4 to 5. So I see 1 over 5 and then 2 over 5 and 3. Yep, so that's doing that. So it does seem to me that if we were going to build an integral out of this, we would start at a lower limit of 2. We want a delta x width. We want the width to be 1, so it would go to 3. And the function that we're working with would be the ln of, well, just plain old x, dx. So the guy that goes from 2 to 3, lx dx, so d should be the right one. Because again, a is incorporating this division by 5 thing, but we don't want that. That division by 5 is just part of our delta x. Part B is starting at 0 and going to 5, but that would give the wrong starting point and the wrong interval width, so it can't be that. And the part C has the right limits of integration, but the 1/5 doesn't want to be on the outside. That all of that is just part of the dx. So that's out of here. And E, well, it has the wrong limits and it is incorporating a shift in our function. We don't want any of that. So that's the best choice for sure. Okay, so to the extra practice ones, we'll do those last few problems now. And again, leaving this one as a multiple choice, hopefully you can see that if we were converting this, then 1, 1, 1, 1 seems to be the obvious place to start our integration. And this numerator of 4 seems to tell me that our width wants to be 4, so our limits of integration should go from 1 to 5. But again, don't be misled by that because we might incorporate a shift. So do I see a 1 to 5? Yes, I see a 1 to 5. But we know that we sometimes might slide this 1 to the left and use the 0 to 4 instead. And I do see the other options of 0 to 4. This one, that would be what, a shift left. So maybe it's B. It could be B. Let's keep investigating and see what our function's doing. But our function does seem to be a simple one where they're just, if they're starting at 1 and adding the delta x times k technically, well, the k is not doing it because the k starts at 1 and only counts by 1. But I'm watching as these things go from 4 to 8 to 12, right? So this is not just a 1 plus 1 over n. Oh no, well it never would have been that anyway. It would have been, sorry, I'm kind of freezing up here. 4, right? The width of our interval is 4, so it would have been the 4 over n times k. So that 4 actually is accounted for because as k starts at 1, you get 1 plus 1 4 over n. Then as k ticks up to 2, you get 1 plus 2 4s over n, which is 8. 3 4s over n. So all that is good. We don't need any other coefficients on x or anything added to x. This expression is just essentially our plain old x. So since our function does not want any shifts, hold on. Now I confuse myself again. So that would mean we want the one that goes from 1 to 5 and then plain old x cubed dx. And then that's not a choice, is it? They all are incorporating that shift of 1. So that means we do need to shift our limits of integration then, because all of these 1 plus x cubed are going to throw things off. Now these guys without parentheses, this might as well say x cubed plus 1. That shifts us up, which we never want to do, so it's not a. Same thing with this one. That shifts us up, so we don't want to do that. Now this one with parentheses might as well say x plus 1 all cubed, and so there's your shift 1 to the left, and we do see our integral, our limits of integration, shifting 1 to the left and going from 0 to 4. So that feels right to me for it to be B as in boy. What's happening with D? D incorporates a shift, but those would not be the right limits of integration for us in D. So we want B as in boy here. All right, let's keep it moving. So the next number 5, which is probably pretty similar to the last one. Again, this would be an integral. If I see a 3 over n, that's making me think my interval width should be 3. If I see 7 plus blah, 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 that's making me think my lower limit should be 7. And with a width of 3, I should go to 10. So do I see a lot of 7 to 10s? Here's a 7 to 10. Here's another 7 to 10. But there are some 0 to 3s. So remember, if we wanted to take our function and shift it 7 to the left, we would end up with a 0 to 3. So of those choices, I haven't eliminated anything yet. It depends on what my function is going to turn out to be, whether my function needs to be shifted or not. So let's see. Why is... Oh, yeah, right. I just was wondering why D was circled already. But yeah, looking at D, that is incorporating a shift 7 units left. But a 7 units left shift should probably be integrating from 0 to 3. So I'm thinking D is not it. And again, I'm not even looking at I'm just kind of eliminating choices. It might not be right to do so. But this 7's on the outside of the function, so that would be a vertical shift. We never want vertical shifts. And then neither of these are incorporating shifts at all. So it's probably then the one that goes from 7 to 10, because 0 to 3 would require us to be shifted over. So I'm thinking that's wrong, but I better double check and make sure by actually looking at the function. Right now I'm just kind of doing process of elimination. But what's the deal? From all these choices I'm seeing, they all have the 7 built in. So that's like our A value of 7. Then it's plus our delta x, which is 3 over n, times k. So yeah, looking at this, none of these have any built-in transformations. So yeah, for sure. No built-in transformations, which means the limits of integration should be using 7 as their A value, and their B value should be the 7 plus 3, aka 10. So it should be C as in cat. And we'll keep going. So for 6, more of the same. So 6, you might want to try to take this and turn it into the sigma notation if that's kind of the way you're comfortable with this. But again, k would still want to start at 1. And how many terms are we looking at? Well, again, if the denominator here is 9, then we should be going from 1 up to 9. And I do have this 2/9 here as my delta x. Then what's going on in all these other terms? Well, I see a 1 over, a 3 plus, a 2 over 9, a 4 over 9, a 6 over 9. So that is our delta x times k. So how would we write that? Well, our width is 2. Yeah, so 2k over 9, of course. But then there is this plus 1 on the end, that one little plus 1. So that seems to say to me that all of this stuff here, that stuff's x, but our function is going to be 1 over x plus 1. Now that plus 1 is built right into the function, so that would not shift our limits of integration in any way. We would still be integrating from 3. We'd still take that 3 as our starting point. And would still take this 2 as our interval width, so it would still go to 5 dx. So even though this function has a built-in shift 1 to the left, it's not affecting our limits of integration because it's built right into the rule. So we would take our original limits from the rule, and then we would only move if we had to, and in this case we don't have to. So it should be that, and which choice is that? It's B as in boy. So yeah, the tricky thing there, I guess, might have been that you might look at the plus 1, and you might have said something like, hey, let's take that away. Oh, I don't want to get it. I'm going to get into double negative territory if I talk about that. So let me not say that. But what you might have said was, since it's been shifted, this needs to shift and go to 2, 4. But that's not true, because the plus 1 was already built right into the rule. So if it's baked into the function rule, then just use the limits that the rule's giving you and don't mess around with it. Okay, moving on. So the answer was supposed to be this, which was option B. Then we move on to the next number 6, and the next number 6 is showing so 100 different things. It doesn't matter how many there are, but we're doing a summation that starts from k equals 1 going all the way to 100. But what are we seeing? We've got the same 1 over 100, and then we're multiplying that by 1 over 100 cubed. So that 1 over 100 cubed, if you're trying to sort of break that down, to me that feels a heck of a lot like an a value of 0 plus the 1 over 100 times k, and then just that whole thing getting cubed. So from our general rule, it would seem to me that this is an integral that's starting at 0, and it has an interval width of only 1, so it's going from 0 to 1. And the function that we're integrating would be, well, again, there's nothing else here. Just all of that would just be plain old x. So this would just be x cubed dx. And we don't need anything else, so that's option E as in Edward. So unless I've done something very wrong, it should just be option E as in Edward. Yep. And is that it? Does that bring us to the end of all the problems? It sure does. So this guy's clocking in at about 45 minutes. I hope that all made sense. I have a sneaking suspicion, though, that it did not all make sense. So again, I pray, I hope that you guys will actually look at this video today being Sunday for you. I hope you're looking at it now so that you can actually start preparing your questions for me on Monday. Again, if you don't, well, nothing I can do to stop you. But come Tuesday, I think you'll be in a world of hurt if you haven't really thought about this well and used every opportunity to ask me questions. So I don't know. I hope that doesn't describe you. I hope that you are in it, doing the work, figuring out what you know and what you don't know, and we'll talk about everything in between on Tuesday. All right. See ya. Bye.